But anyway, welcome back. Hope you guys are doing good today. Reminder, project due Friday. Make sure you're working on those. Tomorrow we'll have some time. If you've got questions, I can help you with it. Or if you want to come after school, I can help you after school, no big deal. But today, our topic, rational functions. Okay, we've been graphing polynomials, but now we're going to switch a little bit and graph what's called rational functions. Our objectives: apply notation describing infinite behavior of a function, identify vertical, horizontal, and slant asymptotes, and then graph rational functions. And then last one, we'll do an application with them. Okay? So let's talk about what a rational function is. Quick definition. Let P of x and Q of x be polynomials where Q of x is not zero. A function f defined by P of x divided by Q of x is called a rational function. It's a fraction. So little small examples here. That's like 1 over x, x plus 1 over x minus 7, and 2x squared over 5x squared minus 7x plus 4. So that's what we're going to be doing today. We're going to be working with these guys, talking about the graphs, what their end behaviors look like. Are there any values that they approach but don't cross? All questions that we'll be answering. First up, let's talk about some notations that we're going to be using. So let's say you find a notation that looks like this. Okay, x as it goes to c and then positive. By the way, c is just a number. Okay. Well, here's how it reads. As x approaches, I'm going to underline that word, c from the right, but not equal to c. Okay? So the plus sign means I'm moving to that number on the graph, okay, from the right, so this way. So what's happening as I'm moving in this direction, and whatever the number is, like 2 or 4, okay? Now we can do the same thing with a negative. So let's say there's a negative sign there, okay? This is as x approaches c from the left. And again, just not equal to that number. We just want to know what's happening, okay? What's the behavior of the graph as it approaches it from the left. So in this direction, so if we're going this direction, and let's say the number was 2, okay, what's happening in the graph as it approaches 2, okay, as it approaches 10, and so forth. Other symbols that we could be seeing, we've already seen this one before. This just means as x approaches infinity. Okay, so in other words, x increases without bound. And then we have the negative infinity. So that's x approaches negative infinity. So it'd be x decreases without bound. And the last two we've used quite frequently, I would say, in this course. But this would be the new ones. Okay, these two notations right there. So let's just put an example to it. That way we can see what this looks like. So I have here the graph of f of x equals 1 over x minus 1 is given. Complete the statements. So as x approaches negative infinity, what does f of x go to? x goes to 0 from the left side, what's f of x go to? As x approaches 0 from the right side, what does f of x go to? And the last one, as x goes to positive infinity, what does f of x go to? Okay. I'll give you a second to copy those down. Pretty much we're just describing, in a way, end behaviors. Okay. So let's look at part A. So as x goes to negative infinity. Okay. Well, let's take a look at that. So here's my x values. So as it's going to negative infinity, what's happening to my function? Well, it seems to get closer and closer to the x-axis, right? But it doesn't go past it. It doesn't go like across it. So it's approaching 0, okay? That's what the parentheses over here meant. It's not equal to that number. It's not equal to 0. It just approaches it, okay? Which is why I underline the word approach, because I don't want people to think it means equal. Now let's look at part B. So here's 0. So let's say we approach it negative. So we're approaching it from the left. So as I'm approaching 0 from the left, I can see that the function is decreasing infinitely, right? So this is going to be a negative infinity. And let me just do this. Because we're just learning it, I'll put up here left. So from the left, okay, what's happening? So from this direction, what's happening to my function? Now part C, I'm going to go positive. So that means I'm going to go to the right. So from the right, I'm coming in this direction. What's happening to my function? Well, it doesn't cross this line. Bless you. But it keeps going up infinitely. So it's going to be a positive infinity is what the behavior of the graph is doing. And again, I'll just put a little note. So this means from the right. Any questions on that so far? Does that make sense? Where we're going from? So plus is this way, negative is that way. Okay, and the last one. As x goes to positive infinity, so this direction, what's happening to my graph? Well, it's getting closer to the x-axis, but it doesn't cross it. And at this spot, that's where y is 0. So it approaches 0, but doesn't actually cross it. Okay. Any questions on reading the notation? Let's keep going. Let's talk about the vertical, horizontal, and slant asymptotes. Let's talk about those next. We touched on it a little bit in the past, but now let's go ahead and dive into it. Consider a rational function defined by f of x equals p of x over q of x, where p of x and q of x have no common factors. Now that's the key part. Other than 1. If C is a real 0 of q of x, then x equals C is a vertical asymptote of the graph of f. definitely underline the word no common factors, and we'll see what that means in some examples here. Now, what this tells me is this. If you look at the graph over here, okay, one of the things you do not want to have in a fraction is a 0 in the denominator, right? That's no good. So whatever makes it 0, that's going to be my vertical asymptote. It's never going to cross that line, okay? The reason for it is you cannot have this be a 1. If you put a 1 in here, you get 1 over 0, no good. So that's why we put something like this. It's dotted because technically it's not part of the graph, but we use it to help graph the function, okay? So that's what this is talking about here. So let's put some examples underneath it. So I got those 3 examples, and all we're going to do is locate where the vertical asymptotes are going to be without graphing it, okay? We're going to find it out ahead of time. You could graph it on, like Desmos, you can graph it on a calculator, and they won't show the asymptotes, okay? Instead, what they're going to do is graph it, and you're going to see the graph like come at an angle and then just like shoot upward. And visually, you could probably graph a vertical line to see what that is. Okay. When I use Desmos, if I had to graph this, if I know what the vertical asymptote is, what I would do is like write it in Desmos, so it plots it, and then I look to see does the graph follow it. And if it does, then hey, I found it correctly. So for this one, what would make the denominator 0? 7, right? Okay. So therefore, I have a vertical asymptote at x equals 7. I'm just going to put BA. So if I were to graph that, there's going to be a vertical line right at 7, where the graph will not cross. Okay, this guy. Well, I have a quadratic, right? So that just means I got to simplify it and see what makes it 0. So I could have more than one vertical asymptote. That can happen. So let's do that. Let's go ahead and set this equal to 0 and solve. Okay, and what I'm going to do is just solve by factoring. So when you factor this, you get 2x minus 1, and then x plus 1 equals 0. Set each one equal to 0 and solve. I could see that x over here would have to be a half, and x over here would be a negative 1. So I have 2 of them in this example. So VA would be at x equals a half, and x equals negative 1. So for that graph specifically, I'm going to have 2 vertical lines. Those are the cool ones to graph, and you'll see one of those. So far, so good. Now the last one, look at the denominator. Now, instead of like blindly solving it for 0, let's be logical about this. X squared is always going to be positive, right? You're adding 1 to it. Is there ever going to be a 0 here? No. So this one would have no VA, no vertical asymptote. And that can happen. Alrighty. Now, let's mess with this guy, the no common factors. Let's say if they do have a common factor, what does that do in terms of a vertical asymptote? So let's try an example out with it. So for this example, okay, we're going to try and see if we can't find. Let's just put if possible, okay? Because not all graphs are going to have that. Not all rational functions will have a vertical asymptote, as we saw in part C. So currently, if I look at this now, what could we say that the vertical asymptote would be? Just 1, right? Okay. However, unlike the other examples, the numerator is a quadratic, right? So here's what I'm suggesting. Before we even jump the gun and say it's going to be 1, okay? Again, if possible, factor the numerator. Then see if there is a common factor. Because remember, vertical asymptotes only work when there's no common factors. So let's do that. So factors of 4 that add to give me -5, well, that's going to be x minus 5. Oh, change that again. X minus 4 and x minus 1. There we go. Okay. Now do you see the common factor? X minus 1, huh? So these cancel. So f of x is actually just x minus 4. So does it have a vertical asymptote?
No.
It does not. You know what it does have? A hole. Let's take a look at the graph. Okay, so here it is. And let's go 1, 2, 3, 4, 5, 6. So this one starts at -4. So 1, 2, 3, 4. Okay. And here's the deal. What did we say originally was the VA before we did any of this? 1, right? Okay. So here's the deal. If you type this in your calculator, do an XY table, 1 isn't going to work. Okay? Just, it won't work at all. But the graph is going to be a line. So how do I show that, even though it simplifies to this, we know originally you're not allowed to have a 1. We put a hole there. So up 1 over 1, I'm going to put a hole because we're not allowed to use that. And then up 1 over 1, up 1 over 1, and then draw my line. Depending on the graphing utility you use, you might not see that. It just depends. I think Desmos does that. I don't know. I can't quite. I gotta look at it. I gotta look at it again. Graphing calculators, the XY table will say like error when you look at it. Okay, so that's how you know. Alrighty. So, any questions on that one? So again, if you have something like that in the numerator, factor it first just to see if there's something in common. Take it out. That's what the function looks like. But whatever it was originally, it's not a vertical asymptote, it's just a hole for the graph. Next, that's vertical. Let's do horizontal. Definition, the line y equals d is a horizontal asymptote of the graph of a function f if f of x approaches, there's that word again, approaches, I'm going to underline it, approaches d as x, again, approaches infinity or negative infinity. Okay? So it's the same situation with this. We don't have to worry about common factors for horizontal asymptotes, okay? So we won't have any holes like that. But what we're trying to figure out is as the graph goes to infinite, like either negative or positive, what's the line tend to go to? Okay? Is there a number that it approaches? Okay? Now one thing I want to point out to you, and I'll tell you what, let me just draw a generic picture here. Something like that. So that dotted line would be on horizontal asymptote. Again, it doesn't cross it, it just approaches some number, okay? So this would be your y equals d, and d is that number that's approaching to. Important to know. Okay? The graph of a function not cross a vertical asymptote. It just can't. And the reason for that is because it makes 0 in the denominator, which is undefined. However, it may cross a horizontal asymptote. So I'll abbreviate with HA. So ba and ha. So just keep that in mind. And when we officially graph a rational function, once we get all these techniques down, we'll talk about this as we're graphing it. Does it cross it? So in other words, like maybe this line comes up here, crosses it at this point, and then just levels off. Okay? Let's get to it. Now there are a couple rules when it comes to identifying these. They're not as straightforward as vertical asymptotes, okay? So let f be a rational function defined by, and I'm just going to make a polynomial and a numerator denominator. So we've seen this notation already. I'm just using the generic form of polynomial in the numerator denominator. I use different variables, that way it doesn't look like it's the same one. So the a's are the coefficients in front of all my terms, and n is the degree for all my variables. Down here, b is the coefficients in front of all my terms, and m is the degree for all my variables there. Okay? So here we go, the definition. F of x indicates that n is the degree in the numerator. I'm just writing down what I just said. And m is the degree of the denominator. Okay? Just, again, pretty much what I just stated there. Here are 3 cases, or 3 different situations for horizontal asymptotes. Okay, so here's the first one. If n is greater than m, now let me just stop there. What I'm talking about is if the largest degree in the numerator is larger than the largest degree in the denominator. Okay, that's why I'm using n and m. So these are talking about the degrees. Okay? Then f has no ha. Every time I write this stuff in my blog, I just keep ha, ba, ha, ba. But yeah, no ha. Okay? Now, why is it the case? We'll talk about that a little bit later. Right now, just know if this is larger than the bottom, then no horizontal asymptote. If the degree in the numerator is less than the degree in the denominator, then the line y equals 0, and remember what that means, that's the x-axis, is the horizontal asymptote of f. Okay? So again, if the degree up here was smaller than the degree down here, then the x-axis will be our horizontal asymptote. Now that would be the very first example I showed you, okay? Where it was crossing, it wasn't crossing, it was getting approaching the x-axis but not crossing it. And the last case, what if they're equal? So if the degrees are equal, then the line y equals a sub n, b sub m is the horizontal asymptote of f. Now, let me put a small example underneath here so you can see it. So example, okay, let's say you had 2x squared on top and a 4x squared on the bottom. Okay, so notice that these degrees are the same. So therefore, whatever the x is, it's going to cancel out, right? These two will just be gone. So the only numbers we got to be concerned with was the coefficients out in front. That's what these are, the coefficients. So this will just be a half. So the HA for this guy is going to be a horizontal line going through a half on the y-axis. Okay? Any questions? Yes?
That word, definite. Is it definitive? Definite.
Definition.
Oh, okay.
The O and the N kind of, sorry.
That's
O and the N just kind of got squished together there. Okay? So let's make a couple notes here, and then we'll try some examples after. I'll put this over here. So let me just, and this is just, again, I'm putting this right underneath those three rules that I just put there. So if you had something like this, so looking back at our first rule, okay, if you had something like this, x to the 6 plus x to the 4th plus dot 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 dot, whatever it is. On the bottom, you get x to the 4th plus x cubed plus, again, I don't care what the rest of it is. Looking at the largest powers, x to the 6th, x to the 4th, okay, I can see that this is larger than this guy, right? Okay, the degrees are. So what you're gonna do, ignore the rest, and this sounds bad to say it that way, but the reason why we're not focusing on that is because just like when I taught you about end behaviors, this is going to dictate what the graph's going to do because it has the largest power. So as x is 1,000, a million, this is the term that's going to be making the most effect. Same thing with x to the 6. So I'm only worried about these two. I'm just going to put a little box around there. So if I were to reduce that, it reduces to an x squared. So what we can say is the graph will behave like an x squared function. Now here's the key part, it's behave. Doesn't mean it's gonna look like it. Okay, it's just gonna behave like it. So I'm talking about end behaviors. Let me give you another example. So looking back at rule number 2, that's when the degree in the numerator is smaller than the degree in the denominator. Let's say I had this, x to the 4th plus x cubed plus dot 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 dot. Then we have x to the 6th plus x to the 4th plus whatever, okay? Again, we're looking at the largest powers. So that's these guys. So notice that the degree is smaller than the denominator. If I were gonna reduce that, that's gonna be 1 over x squared, okay? So the graph will behave like a 1 over x squared function. And again, keywords just behave like it, okay? And the last one, so looking back at rule 3, let's say I had this function, so 4x squared plus whatever, on the bottom 2x squared plus whatever. I'm just looking at the largest powers. So now they're equal, right? So just like what I said over there, this large term and this large term are going to be the same, so you can reduce those would be gone, and you just have 4 over 2 to worry about. So that's going to be the same as 4 over 2 or 2, okay? So that part, when it comes to the horizontal asymptote, will behave like y equals 2 as x becomes large. Okay? This will make more sense when we actually do an example, but I'm just trying to make sure you have something of a reference next to these 3 rules here. So let's go ahead and look at some examples. It's a a lot to keep track of at first. It is. So find the horizontal asymptotes. I'll put here if any, because maybe there isn't. As we saw with rule number 1, there might not be any. For the given functions. So let's start with A. The numerator, well, has no degree, huh? There's no variable there. But the denominator does. So that's going to be a case where the degree in the numerator, which there isn't really any, is less than the degree in the denominator. So what would that be for us? Well, then the line has to be y equals 0. That's where your horizontal asymptote would be. Okay? And, oh, what the heck, I'll show you what the graph looks like underneath it. Just a small little sketch. It looks something like this. Where it just it's just on top of the x-axis like that. It doesn't cross it. Okay, next one. And let me just put a color here. I'm only focused on the largest terms in the numerator and denominator. And we have a third on top and a 1 on the bottom. Okay, so looking at that, that is rule number 1. So n is greater than m. So in this case, there would be no horizontal asymptote. And let's think about that for a moment. That tells me that no matter what number this is, okay, the top number is going to be the largest, right? So is there going to be any restrictions in that case? No, none whatsoever. Okay, it's not going to approach anything. So looking at the graph, it looks like this. So as you can see, it crosses everywhere. There's no horizontal line where it doesn't just approach and not cross, or approach then cross. Doesn't work. Okay, last one. So here, there we go. Those are the largest terms. And notice that both the powers are the same. So that's n equals m. So that means I'm only going to look at the coefficients. So the coefficients would be 4 over 2, which is just 2. Okay? So this graph has an HA of y equals 2. Let me just put HA over here. I was trying to be creative when I made these examples. This one looks really cool. There we go. That's what the graph looks like. And this one does cross. It's good to have an example like this. This one does cross the HA, but then it levels out and it just keeps going along that HA infinitely. This one doesn't cross the HA on this side of the graph. It just goes close to it, that approaches 2, but does not cross it. So there's a good example of seeing one that does cross and part of the graph that doesn't. All right. Any questions? A lot of rules to consider. I think the vertical one's the easiest just because it's like what makes the denominator 0. This one just takes a little bit of practice. Now, I want to look at part C a little further. So here's our next example. Given f of x equals 4x cubed minus x plus 1, 2x cubed minus 1, determine the point where the graph crosses the horizontal asymptote. So looking at the graph, I already showed you that it does cross it. Let's see if we can't find that point. how do we find it? It's actually pretty simple. Where does this line, y equals 2, and this function intersect? Just set them equal to each other, right? So let's do that. So we have 2 equals 4x cubed minus x plus 1 over 2x cubed minus 1. By the way, I mean, we know the answer it is going to cross, but when you approach something like this and it doesn't work out, you get an answer that's like not true, then it just doesn't cross. That's all. Okay, you didn't do nothing wrong. So we're going to go ahead and multiply both sides by 2x cubed minus 1. Helps us get rid of the fraction. Now on this side, let's multiply that. That's 4x cubed minus 2. Okay, on the other side, these reduce. I'm left with 4x cubed minus x plus 1. Okay. I got terms that are canceling out. Those are gone. I'm left with negative 2 equals negative x plus 1. So at first, it might seem like, I don't want to solve that, but it does come out nicely. Subtract 1 over, and then divide by negative. So at exactly, I'll put on the graph here since it's already there. So at 3, well, we'll just write the point. So it'd be 3, 2. Okay, so this is the point where the graph crosses the HA. Because remember, the horizontal asymptote just means where is it approaching, okay? So it's okay if it does cross it, but at least you know where most of the function is going to be ending up when you're going to infinity. Okay, we got one more to talk about. But any questions on horizontals? So far, so good? Okay. Some of you look like you're in torture, so I'm sorry. Like you're in prison, like this was your prison sentence. You got sent to a college math class to learn this stuff. Smile a little bit. It's okay. Nothing wrong with graphing, right? Okay, maybe there is something wrong with graphing. Nah, honestly, I'm feeling the same way today. I'm feeling kind of tired. At least the sun's out this time. It was raining not too long ago, but at least the sun's out. There's a positive. So what's a slant asymptote? Okay, so this is an asymptote that is neither horizontal or vertical. It occurs when the rational function has a degree in the numerator that is exactly 1 greater than the degree of the denominator. And let me just put here exactly 1. Okay, exactly 1 greater than. Okay. Now, to find the equation, I'm going to say essay for that one. I know, quite clever, huh? Divide the numerator of the function by the denominator. The quotient will be linear, and the essay will be in the form of the quotient. But I'm going to put something in parentheses that's pretty important. Not the remainder. I'll explain why afterwards. But so what you're going to do, if you have a situation where the numerator is just 1 degree larger, okay, exactly 1, than the denominator, then you have an SA, okay? And how do you find it? How do you find that equation? You divide them. And whatever your answer is, that's the equation. You're not going to worry about the remainder, though. I don't care if it has a remainder, you're not going to use it to graph it, and again, I'll explain why once we go through an example. Okay? So speaking of that example, let's put it on this board. Start with something that's, I think, relatively easy. Nothing too complicated. Just 2 terms on top, 2 terms on the bottom. I'm going to circle the degrees. So this is a 2, and that's a 1 there. And it matches what I said over there. Okay, the degree is exactly 1 larger than the denominator. Okay, so we have an SA because of that. So how do we figure out the equation for it? We use division. So x minus 1 into x squared plus 0x plus 1. Because there's no x value, so I got to put 0 as a placeholder. So let's do a little bit of long division. I haven't done that in a while. Okay, x minus 1 into x squared, that's silly. That can't work. X minus 1 into these 2 terms, that can work. And it's just going to go into x times. So x squared minus x. First term cancels, the second term is just going to be a positive x. Bring down the plus 1, and I think it goes into it 1 time. So we get x minus 1, subtract, we get a remainder of 2. So my answer is x plus 1 plus 2 over x minus 1. But, as I told you over there in red, ignore this guy. Okay, so your SA is y equals x plus 1. Now, ooh, that was a weird one. Try that again. Why do I say ignore it? Well, here's the deal. As you keep putting in x values, 1, 2, 10, 100, 1,000, and so forth, the bottom part of this fraction is going to get larger and larger and larger, right? Well, if this keeps getting larger, this whole fraction is going to tend or get closer to 0. So this is going to have no effect on this guy, is what that's coming down to. Does that make sense? So again, because this number in the denominator, as you keep plugging in x values that are larger and larger, 2 over that large number gets closer and closer to 0, okay? And because of that, this has little to no effect on this guy. So we're only focusing on this as my slant asymptote, okay? Now, let me just show you underneath just a small little graph of what that looks like. Okay? So we have let's see, what's the start at? 1. Yeah. 1. Just plot a couple points. So there it is. There's my SA. Now this does have a vertical asymptote, right? It can't approach 1, so we're going to have another asymptote here. Okay? And then what you would do is you would plot points. And just for time's sake, because we're going to do an example where we do plot points, but this is what it would look like when you're done plotting those points. So something like this. Which, that's pretty cool. We haven't seen a graph like that before. And again, these will approach but not really touch those asymptotes right there. Same thing with the one on the bottom. Okay? Any questions? So far so good? Yep. Okay, so let's actually graph one. Let's put it into practice. What I am going to give you guys is the steps of how to graph it, okay? I'm gonna give that to you. That way you don't have to worry about writing all these down. I'm just gonna jump into graphing it. But at least you'll have this next to you when you practice this yourself. Because as you can see, there's 8 steps on here. Once you do a couple of them, you get a rhythm going, and this is no problem. Is that? Yeah, that's perfect. So we got our steps. Again, I'm not gonna write them on the board. We're just gonna jump into an example and see it in action. And I'm gonna start here. So let me just get rid of this. So let's put it all to use. So we're gonna graph f of x equals 3x squared plus 2x minus 1 over x minus 1. I think one of the things that's kind of intimidating is once you learn all that stuff and you get an example and like, go. See what you can do. It's a lot. It's like, where do I start? So here's the easiest thing. Start with the y-intercept. That's easy to find, okay? You just gotta plug in 0. So let's go ahead and do that. So just plug in 0 for x. See where it crosses the y-axis first. Well, the numerator is just going to be a -1. Denominator is a -1, so it's a 1. So my graph is going to cross at 0, 1. Hey, we got 1 point on the board. We need a little bit more information, but we got somewhere. Okay, 2. We must find the x-intercepts. So that's when y is 0. Bless you. So let's set the whole fraction equal to 0. If I multiply, to get rid of the fraction, I'd multiply both sides by x minus 1. Well, because that's 0, that just goes away, huh? 0 times anything. So all I have to worry about is the numerator. Okay, when is this guy 0? And we could solve that pretty quickly by factoring. So when you break it down to its factors, it's 3x minus 1 and x plus 1, just like that. So therefore, x is a third, x is a -1. So we just found our x-intercepts. Okay? I know, a third's like, really? Does it have to be 0.33? Yeah, it has to be. But that's okay. We can at least gauge it, right? At least put a point there and say that it's roughly there. Now, what's the next thing I should do? Well, let's look at our vertical asymptotes, right? So first off, I know what this is factored, right? Does this have any common terms with the denominator? No, so there's no holes. So that does have a VA, so it's at where x is 1. That's where you get a 0 in the denominator, things blow up, so we don't want that to happen, okay? Now, next step, ha or sa? Okay, what's it gonna have? Well, let's take a look. Look at the degrees. This one's larger than this guy, right? Okay, so is it larger by a lot or larger just by 1? By 1, so it's an SA, right? Okay, so it's an SA, it's a SA. Very mathematical term. Imagine presenting a math paper and saying those words. Those people look at you like, this guy has no idea what he's talking about. So because it has this, let's divide those and figure out where that equation is going to be for the slant asymptote. Okay? So let's do a little division. So x minus 1 going to 3x squared plus 2x minus 1. Okay? So let's see. First would be a 3x, right? Because that gives me a 3x squared. First terms cancel like they should. This will be a 5x. Okay, bring down the -1, and that looks like a plus 5. So it gives me 5x minus 5. 6 is the remainder. Nope, not 6. Let's try that again. How about 4?
Wouldn't it be -1? Oh wait, never mind. Never mind.
That's okay. You're all right. Now, I don't care about the remainder because I said like that remainder, when you write it as that quotient, it's going to get smaller and smaller, so it's like 0. So we're only focusing on this part. So my SA is y equals 3x plus 5. So that's that diagonal line that we're going to graph in a bit. Now, for step 5, I'll put it over here. Does it cross it? Right? We got to figure that out next. So step 5. Does it cross the saw? let's see. So we're gonna set the slant asymptote equal to the function and see if they intersect. And by the way, it's perfectly fine if they don't. Okay, that can happen. We just want to know if it does. So it looks like I'm going to multiply both sides by x minus 1. So on the left-hand side, I got to expand that a little bit. That's okay. That's going to be a 3x squared minus a 3. And then we're going to have a 5x, and we're going to have a minus 5. Okay. So, oh, I forgot an x there, didn't I? There we go. On the other side, it's just our numerator. I can tell you right now, this doesn't look promising. So that's good. It's not going to cross it, but here's why I'm saying that. So this is 3x squared plus 2x minus 5. I have some cancellation that's happening. Now what's left? Negative 5 equals negative 1. No, that's not true. So it would be a nope. Doesn't cross it. Okay, next thing. Symmetry. Let's see if it has y-axis symmetry. So remember, that's like saying it's an even function. Okay? So plug negative x in, see if it comes out to be the same. If it does, hey, we can use that to help graph. If it doesn't, that's okay. It just can't be a tool that we can use. No big deal about that. So just plugging negative x into it. And let's see, the numerator, that's a 3x squared minus 2x minus 1. Negative x minus 1, that does not look like the original. So, no good. This is a no. So I can't use y-axis symmetry to help graph points. Let's see if it's an odd degree function. Does it have origin symmetry? So let's find negative x. And if it equals that, then hey, it has origin symmetry at least. Well, I'll tell you right now, the answer is no. If I distribute a negative to all three of these terms, it's a negative 3x squared. Well, this is a positive 3x squared. So already, no. So I'll put here, this is no y-axis symmetry and no origin symmetry. So, that happens. It's not a big deal if it happens. It just happens. If they did exist, then I can use a little symmetry to help. Okay. Now, last thing, let's plot points. Let's talk about that, okay? Now, how do I do this? It's actually pretty simple. Let me just draw a little number line right here. Well, not a number line. Let me just go ahead and draw a small little grid, I should say. Okay. I have a VA at 1, right? Is that what it says? 1? Yeah. Okay. So there's that. I have a y-intercept at 0, 1. So up here, and this isn't going to be the official graph, by the way. And then the x-intercepts would be a third and negative 1. So how do I, plot additional points to help me graph the whole thing? Well, it's pretty simple. Break it up into intervals. So from here to here, we'll call that interval 1. Okay. Then from here to here, from this x-intercept to the y-intercept would be interval 2. From the y-intercept to the next x-intercept would be interval 3, and then over here would be interval 4. And what I'm going to do is just pick a point in each interval, like pick an x value, plug it in, get a y coordinate, and that's going to help me plot additional points to see what the graph's going to do. Okay? So let's go ahead and do that. So over here, I'll just put interval. I can spell it. So 1, 2, 3, and 4, and these are the points I'm picking out of there. So let's see. Negative 3, let's see, in this interval I picked negative 1/2. The third interval I picked 1/2, and the fourth interval I picked 2. Again, you can pick any point you want, I just picked those ones. So I just picked negative 3 over here, was it, negative a half, because there's not much to pick from, half over here, and then I picked 2. So when you plug those into the original, you get the following outputs. So you get negative 5, 0.83, negative 1.5, and 15. So in conjunction with the x and y intercepts, the VA and the SA, I'm going to plot those points as well. All right, let's sketch it. So let's start with over 1. So y-intercept, right? So 0, 1, put a point there. X-intercepts, so roughly here, and negative 1, 0. Let's see, the VA was 1, so let me just draw a dotted line at 1. Okay, that's where it just can't cross. Now let's graph the SA, so the, what was it, 3x plus 5? So 1, 2, 3, 4, wait, 1, 2, 3, 4, 5. There we go. So up 3 to the right 1, down 3, 1, 2, 1, 2, 3, left 1, 1, 2, 3, left 1. So we'll draw another little, well, my graph's not going to be too symmetrical, but we're going to try it anyway. There we go. Okay. And then my last step is to plot my additional points that I just found. So negative 3, 1, 2, 3, and negative 5. 1, 2, 3, 4, 5. Negative a half in 0.03, so right in here. Positive 0.83. I was wondering why that looked weird. Half and negative 1.5, so somewhere here. Okay, and then 2 and 15. So 2 and 15 will be somewhere up here. So now we just connect them. Now you guys are going to have graph paper, so it'll be a lot more accurate with you. And then this will come down here and bounce back up. Okay. There it is. Cool looking graph. Now, could you plot more points than this? Yes. Okay. I knew what the graph was going to look like up here just from experience, but you can plot additional points if you do. Alrighty. So that's graphing. Tomorrow we'll do one application. I didn't get a chance to do the application problem, so I'll show you one of those tomorrow. It won't be a big deal. That's all it takes. Don't look away. If you look away, you're gonna get lost.
What does any of this even mean? There's like brackets on
I got everything except once he started grabbing it too much because the interval mainly.
If not a single person gets those questions right, he said he was going to do that.
Like, honestly, I don't even think I would. Doing this in reality, I don't think I would worry about too much of symmetry.
I don't.
I just plug in, find it. Yeah, glue. I kind of want to cut this out.
I need a closer look. What am I looking at?
That's not my fault. You can get up and move.
What's this?
I was picking intervals and then picking a point in the interval to graph an additional point here. So this is these are my x-intercepts.
Okay.
This is my y-intercept, and this is my VA. So I was literally
You chose something for that x-intercept, between the x-intercept and the y.
So
the y and the x-intercept.
the vertical.
Past the vertical.
yes.
Those are your those.
Yep.
And then the intervals you picked.
Yeah.
It's just
Just in between
random
those
points
ones.
somewhere on
Yeah.
this spot.
So I picked like -3 over here. I plugged it into function and the other was -5. So that's an additional point I was gonna put.
Okay. So you got -3 wherever it is. So, okay.
Yeah.
And then you plug in -1/2.
To get 0.83.
Is within this
That
interval,
yeah.
which was the 0 and the.
And technically I could have 5, like I could have plotted an additional point here. I was just trying to go for the big
And then the third interval, which is
between
this.
those, which is very small, so I got a half again. And then I picked 2. Yeah. At least I could technically have 5. I could have put 1 point. That's all I needed to try. So got my. So what I did first is I plotted all those points I found.
Oh.
I plotted my VA and my essay, and then I plotted all these points, and then I just
I get it now. It looks very odd from where I was sitting.
Honestly, I'd probably plot 6.
yeah.
Isn't it today?
For the,
I would yeah
This
I'd
one
probably
and
put
for
2
that
more
one.
on the top.
What the heck?
But again, timing wise, I mean I probably could have picked a couple 2 there. But
Okay. I'm gonna have to write that down later.
sure. So you do an N and 3 minus 4. So you plug 1 in.
they left without their homework.
Who was that?
Whoever sits behind Jalen.
Well, I think I ran into Andre, so I think
It looks horrifying.
Yeah,
they're both back there.
Yeah.
But Andre was back there. Leo sits next to Andre on the other chair.
That's not my problem. I don't talk to him, so I don't really do that games that bad.
Okay, so here's the it's so right here on this side. It's
Justin, do you have a glue stick?
1 means what's the first
No.
number over here? If it was a 2, you would
Trying to
have
glue this in.
Blue what
Does
is?
that make sense?
Oh.
If this was a 3, check P of 3 is true.
Oh.
You'd be adding these 3.
Cut it out and glue it in.
So P of 1 is just 1.
I don't know, I think it'd be easier.
That's
Nice.
when you get the 1 equals 1.
You know?
I feel I need to get glasses. Like I need to.
Dude,
get my
yeah,
glasses.
you
My
say you keep
So
procrastinating.
this
Stop.
side, left hand
is
side,
actually hurting
P of
trying to
1
read.
is the first term you see.
So
Tell your mom or dad
On
to
the
get
right
some
hand
glasses.
side, you plug 1 in correct.
I
That's
already
good.
have 3
And you
frames that
simplify,
I picked
that's-
out. I just
So
need to
go
review them.
get them.
I just need to review them with my
Okay,
parents
so
so we
here
can
you
order
did
them.
this, which is good.
So get them.
Here you did 3K plus 1, which is 83K.
Justin, do your
3.
parents know how to do math?
Okay. So you add that to
My
the other
dad's
side,
okay
put
at it, my
1,
mom's
find the
not
common
good.
denominator,
My mom is not
simplify,
great.
Can
My
we do
dad
that
knows
one
his
in here?
stuff.
Can we do that?
It matches
Math's
what
right
you
there.
have here, which is good.
My dad?
Be true.
Okay.
I don't know if he
That's the only
remembered
thing I
how to do it. He might have
Very good
remembered
at
doing it.
Yeah, that's what my dad says. Every time. I'm like,
I feel like when you're out of the loop with this kind of thing for a while.
I think I should keep all this in.